Let's discuss conservation laws and the control volume method. The law of conservation is fundamental in a lot of physical and engineering systems. So to apply conservation laws, we first needed to introduce the concept of a control volume. Volume is a physical space that is to analyze the system you are looking at. For example, the fluid flow, heat transfer, mass transport, or energy exchange. The control volume provides a structural framework for applying conservation laws. There are two types of control volume. One is called fixed control volume. Fixed control volume, it means the volume is fixed in space. For example, if you have some fluid motion, in space, and you are looking at a specific window or space, and you don't change the physical location of this control volume. You are only looking at like how things move. It's like you are standing in front of the window in your home, and then you look at the kids or the cars drive outside, like on the street, and you are not changing your window, but the kids or the cars are moving across the window, and you are counting how many cars moves into the window and leaving the window, etc. And the second type of control volume is called the moving control volume. So those control volumes are not fixed in space, but move with material. For example, you have some particles of interest, and you would like to study their behaviors. At initial time or at one time, this is the control volume because this is the control volume that includes the particles. This is at time t. And at a later time point, those control volume move to a new space. And you draw a new control volume. It's the same set of materials, but the arrangement of material changes with space. And then that's also the control volume. We change the shape of a control volume. That's called the moving control volume. So the first type of control volume, which is fixed in space, we call it Eulerian approach. Which is used a lot in fluid mechanics. The second is called the Lagrangian approach. Which uses a lot in solid mechanics and elasticity, or plastic body, whatever, in solid mechanics. So for our class biotransport, we will use a fixed control volume in almost all of our chapters and examples. So later on, we will derive, for example, the equations of fluid in a pipe or when we derive fixed second law or any diffusion equations, we will at every time we will need a control volume, and those control volume would be fixed. So when we apply or use conservation laws, we usually study it in the context of a control volume. What we are going to do is we look at the material live in and out or being generated or consumed within the control volume, and then look at how do they change over time. So the general form of conservation law is expressed in the following balance equation. We have balance tells us accumulation equals to in minus out plus generation minus consumption. The accumulation refers to any physical quantities that you are studying. If you are studying the conservation of mass, then the accumulation means the accumulation of mass within the system. If you are studying the conservation of energy, then the accumulation refers to the accumulation of energy within the system or within your control volume. And the in and out means the material or the quantity you are studying, either heat or mass or energy or momentum, whatever, what you are studying with, which is move across the control surface. So the in and out means across all the terms across the control surface. And then generation and consumption refer to the terms or the mechanisms that happens within the control volume. In many of the dynamic systems, we usually don't use this balance equation itself, but what we are using is the differential form. So for dynamic analysis, use the differential form. Means we are looking at the time derivative of each term. For the rest of this course, we will use it a lot. And I'm not going to redo these examples again and again. Well, every time I use it, we will solve a new problem. But for today, we are not going to touch anything like fluid mechanics or diffusions that we will discuss later. But rather, we will talk about the two examples which is not necessarily fall in the continuum mechanics regime, but rather some applications in population or in finance. So hopefully you will find these conservation laws being helpful, not just in developing a continuum fluid mechanics or physical quantities, but rather in general for a lot of wider applications. Let's look at the first example of bacteria population dynamics. Let's consider a control volume. The control volume can be your culture dish. So if you are a biologist or studying bacteria populations, and you will have a culture dish, and then you will grow bacteria in it, and that will be a control volume. So you may want to know the population as a function of time in the dish. And let's assume there are two processes that affect the population. One is the bacterial reproduction rate. So we assume that the reproduction rate will be a constant. And also the increase or generation would be proportional to their current population. That means the higher the population you have at any given time, the higher the rate of growth will be. And we also assume there is a prediction term, which can due to any mechanisms, you may have a different populations of group bacteria or other organisms that will eat on it, or you may have other things that naturally degrade by itself. So we just give it a term in general, generic prediction term. We say that it is being removed at a rate k. Now our task is to find p, the population as a function of time, given that the initial condition is p naught. So initial condition means at t equals to 0, the population is p naught. So let's apply the equation we just mentioned for the conservation law, the differential form. So the rate change of the material is d dt. So in this case, the quantity we are looking at is the population. So this is our the physical quantity of what being accumulated. So then on the left-hand side, we have the p dt. On the right-hand side, there's the contributions. So the in and out refer to the bacteria which goes across the control volume surface, the control surface. And since during the experiment, we are not adding new bacteria into the culture dish. And also we are not physically remove or take out bacteria out of the culture dish. So there is no bacteria that goes across the control surface, across the control, the boundary of the control volume. So there will be no in and out terms. The first two terms will be 0. The generation term would be the reproduction term, and the rate of change means the rate of increase of the population into it, which is expressed as degeneration dt. It is the rate of growth, which is the production rate multiplied by the current population. And it also tells us that the consumption terms and or we call the prediction term is at a constant rate t. So it is just p minus k. So this is our differential equation. And once we solve this, we will get p as a function of time. So now, as a differential equation, we can write it in a way which is a standard differential equation form. On the left-hand side, you have your primary variable t and your dependent variable p. On the right-hand side, you have a constant term. Now, this equation can be solved by multiple ways. If you remember from your differentiation class, and you can just solve it on your own. And I'm going to introduce a method which you have also learned, which is called the sum of homogeneous and a particular solution. In this way, you don't need to use any special integration. So let's see The total population is a sum of a homogeneous equation plus a particular equation. The homogeneous equation, sorry, the homogeneous solution plus a particular solution. The homogeneous solution is the solutions that satisfy the homogeneous equation, means the right-hand side of the equation is 0. And then you can rearrange and separate the variable. This is very easy to solve. You will find that it's a constant c multiplied by e to the power of rt. C is a constant to be determined. It will be determined by the initial condition. However, without the particular solution, we are not ready to determine Q or determine C. So we also need a particular solution. The particular solution is any solution. You don't need to worry about how complicated or how complete they should be. It's just any solution that makes this equation true. The general trick is to find a constant. So you would let P to be a constant. Well, if a constant works, sometimes if you get a more involved particular equation, you may not be able to find a constant solution. But for this case, we are able to find a constant solution. So if P is a constant, then the PDT would be 0. So you just need to find the particular solution that satisfies Rp equals to K. So it gives you K divided by R. You can check this particular solution. If you substitute back into this equation, it doesn't satisfy this equation. So this is a very simple form that you can use. So now our final solution is the sum of these two. Now we are ready to determine what is C. We are going to use initial conditions. Means at t equal to 0, t equals to t naught. So which means t naught equal to C. At t equal to 0, then e to the rt would be 1. So it's C plus K divided by R. This will give us C equal to t naught minus K R. Okay, then we find our expression T2. Or you can write it in another way if you would like. So this is an example of using control volume and the conservation laws to study population dynamics. You might have seen this in other contexts like prey and predator models and also disease modeling, infectious disease modeling. Those are very popular models over there that is follow the similar framework. You may not have think about those models in the context of control volume and the conservation law. You may just write out those equations based on how population grow. And essentially what you are doing is indeed following the framework of conservation laws. So hopefully it can give you a different perspective of looking at these type of problems. Now let's look at a second example. It's in finance. So we will see that the conservation laws has wide applications. It's also in other like disciplines. In this case, finance. So let's say if to buy a house, you borrowed total amount of money M naught from the bank, and the bank offers you a loan with a term of N years at an annual interest rate R. It's a compound rate. So what is your monthly payment? And what is the total amount you will pay back to the bank, and how much interest will you pay? So it means you know what is M naught, you know what is N. N can be 5 years, 10 years, whatever. Given N, given interest rate R, and given the principal M naught, what is your monthly payment? Basically, that's what's being asked. And you can also ask other questions, how much interest you paid and how much total you paid. So to study this problem, you can think of a virtual control volume. It's like a system that the money that you own to the bank, for example. And you are going to think about how much money you continuously own to the bank and how much money you pay back in that sense. So you can use M as a function of time as the money you own the bank at any given time. And you want to know how this changes with time, or you want to know what's the differential equation that can describe this. So to think about it from a dynamic perspective, it's harder for you to tell what's the exact amount of money at each amount of time, because you know it changes with time. But you know the rate of change of money, because at any given time, the rate of change is dependent on how much money you have in the bank and how much you pay back. So let's say you want to write out the equation for DMDT. The rate of change of the money you own to the bank at any given time. First of all, if you own amount M to the bank at this moment of time, you know that this money continuously generates interest. So you will have RM, that is the interest being generated, which is proportional to the money you currently own. And however, each month you will also pay paid back to the bank. So you can let P represent the annual payment you make to the bank. So you can say P is your annual payment. And R is an annual rate. So this equation, you can think about it like it's work on a time scale of annually. And if that makes your life easier. However, once it's in differential form, it is generic. So the initial condition, if you see IC for the rest of the class means initial condition, it is M at t equal to 0 equals to M naught. So if you can solve for this equation, and then you will be able to tell what's the money change with time. And then you can also ask at what time you will own 0 to the bank. That means after n years, the money you own would be 0, and we will see that later. Now, first of all, let's solve this equation. So interestingly, this equation has exactly the same form as our bacteria population. So I'm not going to solve it in detail. You can do it as your own. You can figure out that the money you owned to the bank is given by this equation. Now, P, we don't know what is P. P is our annual payment, but it asks us what should our monthly payment be. Well, if you know your annual payment, then your monthly payment would just be P divided by 12. So you are going to figure out the P. Figure out the P in a sense that you want MT is 0 at T equal to M, means after n years, you will pay back everything. So that means Mn equal to M naught e to the R n plus P divided by R e minus C R n equal to 0. Okay, this is an equation which is like an algebraic equation that you can solve for P. Basically, once you set up your n years of loan, then you know how your P should be. So your monthly payment would be P divided by 12. And it also asks us what's the total amount you pay back to the bank. The total amount you paid to the bank is n multiplied by P, because P is your annual payment and you pay back to the bank through n years. So that's how much you pay in total. And your total interest would be the total amount you paid subtract the principal. That's the total amount you paid. Okay, that's our two examples. Hopefully, you would appreciate the conservation law better than you would do for a generic like mass or energy conservation problem in fluid mechanics or in diffusion problems. But we will see a lot of those later in the course. And before we wrap up, let's look at the final problem, which would be an exercise for you or your homework. It's thermal energy balance in a heated tank. So the scenario is you consider water held in a well-mixed tank. The tank is being heated by an electric heater. So you have water flows into the tank at the water. So the inflow water happens at a given temperature and it leaves at the same rate. So the temperature of the water goes into the tank is T in, and the rate, the same volumetric rate F happens both inlet and outlet of the tank. But the tank leaves the temperature may have a different temperature. And you can also think about the tank have a total volume V. That's how you may model the system. And let's see what else the problem tells us. Let rho represent the density of the water and the Cp the specific heat. So you are also given the specific heat capacity of the water. The electric heat adds thermal energy to the tank at a constant rate Q. So it also tells you how much energy is transferred through the water at the tank. The total energy content in the tank at any time is determined by the mass of water in the tank, the specific heat, and the temperature. So the question is for you to determine how the temperature of the water in the tank changes over time. Okay, so this will be your exercise.